recording. So as always, hello everyone. Today we get to cover, well, we cover natural language processing, but a very, very interesting, like huge deal right now as part of ML Weekly. I think that that is worth spending at least a decent amount of time, at least some time covering is AlphaFold. And I hope you'll get somewhat of an appreciation as to why. And it's a very fitting topic because AlphaFold actually has been modified over a predecessor to use transformers, which, if we're covering NLP, is also just a very timely collection of topics. Anyways, as always, this will be publicly recorded. Like general disclaimer: keep video off. Ask questions in the chat. I'm happy to answer as we make our way through. This is also our final tutorial. It didn't really strike me until yesterday, and I thought I still had another one next week. But yeah, this is it. I guess there's like one thing I want to say is like it's been kind of fun. I don't know. I haven't done much like kind of like long-term tutorial type things this way, and I actually have like no idea what any of you guys look like, more or less. Like I haven't seen any of you guys, so it's kind of funny. I get to like present this work to these like nameless people, but I guess it's been kind of fun, like getting to know you guys somewhat throughout the semester. I hope that at least these tutorials and these things have been kind of like fun. And like it's one thing to learn machine learning, but it's such an active and exciting field, and I don't know how many of you actually do plan to end up going down that path. But yeah, I hope you guys actually like gained quite a bit from this and get at least a humbling sense that there's so much that goes on, and there's so much that you guys can do. You're like taking some like kind of fun quotes from Lord of the Rings. Like you never really know where it's going to sweep you off, and actually the like concept of like AlphaFold and like more on the like research side of things, it's moving so damn fast that it's kind of exciting to at least have the opportunity to teach you guys this stuff. And if you guys go on and do like funner stuff later, yeah, I guess it's like it's not really goodbye. I actually look forward to hopefully seeing some of you guys do some really like fun, amazing stuff in this general space. But yeah, anyways, this is our last tutorial. I hope it's been fun. And so without further ado, ML Weekly this week, I like can't stress how really like I call this NLP. This is really like maybe more like machine learning, AI, almost like I don't know, the impacts or what's happened this past week. If you're not familiar, basically DeepMind's AlphaFold2 on November 30th, as part of the CASP challenges, it's the critical assessment of structure prediction. So this is again a biology type problem, but basically DeepMind solved this, and this has been like a grand challenge for 50 years. And before jumping too far into the article, this has like some really significant implications, not just for like biology, not just for AI, but like just, I mean, how AI is being brought to actually, you know, we always say we'll solve all the like big world problems. This is actually one that wasn't expected to be solved for another couple of decades, and yet here we are. Like it's 2020, and yeah, there's a lot of bad news going on, but this is something that wasn't expected to be solved for another like 5 to 10 years. So this is actually the biggest advancement, I guess, in structural biology in 20 years, but it's also simultaneously the biggest advancement in AI. Well, there's a number of huge advances in AI, but this is one where we're actually, much like when we saw against the, I guess, Deep Blue basically beating Kasparov in the 90s, when people thought, wow, like I mean, chess has been solved, and then Go has been solved. It's always been AI's kind of has been like a very, very exciting development in basically like solving these massive state spaces, right? Like chess has like 10 to the 100 or something number of possible games, and it's just like it computationally was like inconceivable that you could develop a system to ever you know, solve that. Go is an even greater state space, and that's the thing. It's now being brought to an actual real world problem that has like huge consequence for drug design and like medicine and so on and so forth. So this is kind of like a very like inflection moment, I think, in the fields. And like one general prediction is that I think this becomes a candidate actually for the first Nobel Prize eventually, maybe not in the next couple of years, or at some point in the next couple of years, but it would be for the first time a Nobel Prize that would go to a machine learning model. So it's like most of the work for for a Nobel Prize is like, human in like intelligence endeavor and like solving a problem. Whereas here it's just like, it's teaching a thing or like framing it in such a way that it can solve that problem for us. But because this has such like great ramification down the line for life sciences and medicine, this is what I expect. And it's pretty huge. The reason why it's so difficult, like protein folding, for those who are unfamiliar, is taking like the sequences that we're looking at, the like primary amino acid sequences. Proteins take that like linear sequence of amino acids, and then they have to figure out how to like basically like form a functional unit, basically a functional protein, to then go on and actually do things within a cell. And the space, like the space of possible conformations is like 10 to the 143. It's just this like massive state space. And there's this like very well-known paradox, the Leventhal Paradox, which is like, why is it that life, like basic biology, is so good at this when the state space is so large? Like they can, like as soon as they come out, they basically like fold within a fraction of like on the levels of like milliseconds. And it's like basically life has Josh Schreier says, all my contributions to folding at home invalidated. Yeah, actually, so folding at home is, for those, again, who aren't familiar, is basically, it was like a massively distributed way to try and kind of like gamify protein folding. Like people could actually like help generate like kind of like predictions as to how a protein might fold. And it's like, it's been this like massive kind of like global level effort. And the CASP competitions in particular, it's like there'll be hundreds of teams. And I remember seeing a lot of lectures by some of like the leading scientists working in this space. And they're just like year after year, they'd be like, we've incrementally like solved these like minor issues, but like, or like these like incremental yet important issues. And yet it's just like through deep, massive reinforcement learning to just like learn this massive folding state space, and like the process to fold into that space, like by just pure compute power alone. Anyways, we'll jump. I'll actually show you the figures. It's just like it ends up being this like very massive undertaking, and this is why it's like it's going to save so much money and like accelerate. Yeah, watershed moment, as Stefan says, is exactly right. It's now as good as generating the X-ray crystallography, basically like when you try to experimentally determine what the structure is, you do what is known as X-ray crystallography for just one protein. This is usually on the order of like $120,000 and usually takes about a year. And this is actually why most of my research is sequence-based, because we know so few structures. They're like, if you want to study organisms, you want to study like biology, or like molecular biology of an organism and make predictions at that level, you couldn't rely on having a structure just because of this. Like people can't, like, this is just not scalable to like hundreds of thousands of proteins within a given organism. So like it would take hundreds of thousand years, or like massively parallel. Anyways, it's like there's all this stuff, but if we can predict them now to the same degree of accuracy as you would, or actually if you can deduce it in exactly the same way as you would get through X-ray crystallography, we've actually just like blown open all the space of being able to use like structure-based predictive techniques to study molecular biology, which is like a huge deal. Like I never thought, well, at least I'm still in my PhD, but like I never thought even to see this in like the next 10 years, let alone, yeah, near the end of my degree. But anyways, all to say, let's actually, maybe I want to show you guys. I strongly recommend at least reading the blog post. There are some skeptics out there that are like trying to like figure out if this is indeed as impactful as it truly is. I mean, this is huge for DeepMind in the sense that, like, you know, they've been working anyways hard to get to a point. Anyways, this is kind of like the takeaway graph. So on the x-axis, this is basically just like a measure of correctness when folding proteins, and it's considered that if you get to basically 90% like GDT, you basically have folded as accurately, or like at an accuracy that matches basically X-ray crystallography. And like you look at CASP-7 in 2006, it's like, oh, we did decent. Well, we did a bit better in 8, but it's like over the years, it's kind of like fluctuated around this point, which is why people were like really surprised when we had in 2018 the first AlphaFold. Like this was a margin like jump. And I remember in 2018 people were talking about this specifically. It was like a pretty significant improvement, and then the improvement in 2020, like basically in the span of, I guess CASP or DeepMind started getting into this around 2017, like literally in the span of 3 years, they solve it, which yeah is pretty impressive. But the other thing too is you have Google level infrastructure to do this. So I think that's one thing. Like a lot of this goes back and says like they beat out 100 other teams and so on and so forth. But most of the research teams, I think, working previously just didn't have access to this level of computability or compute power, which I think has this other kind of deep ramification that like some of the biggest research, I guess, companies now are going to be the ones kind of forging forward. It's like it almost takes away from the academic, all the academics in these hundreds of research labs and teams. It's just like you just don't have the resources to compete. Although these research labs also, they work a lot with universities and whatnot. Like there are a lot of like previous CASP experts that are basically consulting on these types of things. But anyways, it's all to say like it's a really exciting development, and to be learning machine learning now while these things are coming out is just like, I know, I hope you guys get excited by it. I hope at least, if it's always good to go into industry and all these types of things, there's a whole lot of like problems to solve there as well. But there's like some very real world like research work. Anyways, I'm just very excited by this, but I've also like worked predominantly in this stuff anyways. All to say, I strongly recommend you guys like read up on this. There's like the long term, honestly, what I predict longer term, if we start, I'll just touch on this, as we start making things more and more, what sort of areas does this influence? Basically, you can, like a lot of cancer drugs, like personalized medicine actually in particular is one. Like many drugs are designed with like a one size fits all for most people. It's like, this medication is not working for you, try this other one. It's like very trial and error. Whereas what you want to do is if you can like get a readout of someone's specific proteins and like their specific like conformation, and you want to design a drug that specifically binds to them, like you couldn't kind of like get all the possible variations of foldings or like modifications or mutations of a given individual. So you just designed for like on average it will be best. This opens up basically within medicine this whole potential subsequent field of like personalized medicine. So you can actually design things specific to an individual. I don't know how like scalable that will end up being, but like the reason why it wasn't being done was predominantly because of this. Yeah, so medicine's going to get a huge uptick, like studying just like basic biology. Like you can only go so far to like understand, what happens molecularly without actually knowing how do the actual functional things work. So there's like kind of like heuristics and like different type of modeling and stuff that you can do. This basically just, it literally just revolutionizes the entire field of like basic biology. So that's exciting. Nice to be kind of on the computational biology side because you keep like working in towards these types of things. Anyway, by making it completely end to end as well, it's also going to open up, I think, opportunities for like artificial life, like actually simulating basically lifelike systems computationally, like in like, again, a bit of a modeling way, but we'll actually be able to like tune and tweak parameters of that system. And like, anyways, it's with respect to like just AI, like actually generating an artificial, not just like intelligence, but artificial life. This will really help to that end. But anyways, I don't want to belabor the point too much. We do have a lot still to cover. But yeah, this is really friggin' exciting. So all I have to say, we go into the notebooks. I don't know if Jim mentioned, I'll probably hop into the last class next Thursday, more in the sense of, I think he's going to review some materials, but it'd also be nice to just like have a general conversation or like kind of like end and of course chat with you guys. If anybody's like interested even like more in this type of stuff, like I'm happy to go on for hours on this stuff. But anyways, all to say, I haven't uploaded these yet, but I'm also trying to maybe like compile these two together. For some reason, Google Colab was giving me some issues earlier today, so we're going to do everything in Jupyter Lab. But because of that, I don't have kind of all the dependencies for everything run through or like set up. So we'll only do kind of like part of it. So there's like a first part that's on basically just like we're going to cover just the things that if you're going to work in NLP, you have to know, which are like basically just like processing text. And then there's tons of applications that you can apply these things to, but the first bit will be on that. The tail end, I don't think I'll be able to run it also because it's a bit longer, but I'll introduce basically Hugging Face. Some of you who work more in the transformer, who've already kind of like toyed around with transformers will probably know this very well. But like Hugging Face is basically like almost, well, a research team, but like also like just a group that's making massively available transformer models, particularly with respect to the NLP field, which is why they're being taken up so quickly and so easily. And they have, well, I'll just like foreshadow it. They have tons of notebooks. Like they literally for any and all application, you can basically like find the one that's closest, like getting started with tokenizers, getting started with transformers. I think the getting started with transformers is, or the how to train a language model is the one that I kind of just like cover briefly near the end. But yeah, if you have, if you ever go on and do anything in NLP, like there's quite literally a notebook there to get you started. So we'll touch on that. The other stuff I'll just like foreshadow comes mostly from this source. So here it's again another towards data science, nice like readout of everything, but it's also worth like literally showing the code for it, because without a doubt, if any of you like start working with text, there's all these concepts that we have to cover. So we'll start with that. So I guess a brief tangential aside as well, for anyone, if you actually plan on actually going and pursuing any like advanced research in NLP, there's a very interesting concept, or well, mystery trend law. There's this, what's known as Zipf's law, which is basically a universal distribution of word frequencies within not just any language, but all languages. There's a really good, for those who follow Vsauce on YouTube, I would strongly recommend, it's about 20 minutes long, but basically Zipf's law is like everywhere, and it's something that props up predominantly in NLP. It's like one of these things that it's kind of like just interesting to know, but at the end of the day, if anybody goes on to this, Zipf's law is probably going to prop up very commonly in your work. So just interesting to maybe like listen to, read up on. But yeah, without any further ado, I mean, like what is natural language processing in general is really basically just the subfield of machine learning that has to do with applying learning algorithms to text and speech. And you might literally be using any one of these like number of times within a day, whether it's asking Siri or Google or Cortana or whoever, whatever your language or your like in-device AI is. There's an element of speech recognition, like basically like it could be something like real-time captioning, which we actually see on YouTube videos. Like Google has set up on YouTube a real-time captioner for basically spoken whatever. Like even my videos are captioned. I like go back sometimes to see if they caption it properly. But anyways, it's like very accurate. When you ask your phone for anything, it's sound waves being absorbed by them, or being recorded by the microphone, that is then turned into a signal that is then kind of cast into the closest word. Like anyway, speech recognition, document summarization, like how do you take, you know, a whole corpus of something and try and like distill it down to the most core, like summary is another. Machine translation is an obvious one. That's just like sequence to sequence, as we've seen before. Spam detection, just like binary classification, spam or not of a given email. Anyway, so on and so forth. Like question answering is another one that's actually kind of interesting as well. It's like given a question, come up with the, like this is very much for those familiar with Turing tests. There are a few question answering bots out there that have already passed the Turing test. what that meant for like is this a watershed moment for AI and so on and so forth was kind of debated then. But yeah, one that you'll probably use a lot when typing is your autocomplete, just like predictive typing, what prediction of what the next word is given the context of what has already been written. You see this in emails now and so on and so forth. So anyways, all to say, there's a lot that you can do, but at the basis of it all, and this kind of just like harkens back to this kind of recurring idea, you need to have good data. You need to have good text and like representative of a given task, but also you need to like clean it up and process it and prepare it in certain ways. So these are the general steps. There are others that are involved, but these are the ones you would likely have to do most predominantly. So if you're just given, you know, a text file with just like a bunch of like either scraped data or represents like a converted PDF into text form or whatever, and it not just like one, but like maybe thousands of documents, thousands of pages. One of the first things you need to do is what's known as like sentence tokenization. And tokenization here is really just like the key like word stem here is token, to basically break it up and to tokenize it into its unit sentences. So it can also be thought as like sentence segmentation. So just dividing a string into component sentences. For each of those sentences, you would want to do something like word tokenization. So again, splitting up each sentence, figuring out what elements are words. So yeah, take a given string of a given language, break it down into component words. You may not necessarily have to break down the sentence first. You can do like word tokenization first. It's just you then lose kind of what you might lose what words went with what sentences and so on and so forth. So basically these usually go in combination. Then there's what's known as text lemmatization and stemming. And both have this, both are like kind of a way to trying to reduce the space of possible words. So when you think of the word drive and drives and driving, these are all unique strings. These are all unique words, but semantically they all like mean the same thing, to drive, or even, whoops, sorry, even past tense, like drove, and all these words. You want to, if you have a huge space where you don't actually kind of like compress it based on the semantic meaning of those words, you actually make the task much more difficult. So lemmatization and stemming are basically two ways to get around that. You can think of stemming as kind of like a crude way to do it. Stemming is usually, it's usually like a lookup. So it's like you'll have a lookup table where it's like, if you see drive, or driving and drives, match it to drive. So it's like a bit of like a heuristic, or it's like if it ends in an ED, truncate the ED so that it's not like something like stemmed, right? So it would truncate the ED and then convert it to stem and so on and so forth. So it's a bit more of a crude way, whereas lemmatization is a bit more refined. It's you actually use a bit more like contextual information to do it. So basically both do the same task. If you had to do one, and you can kind of use them in combination as well, but basically that, I guess that's why both of them are kind of put together. But really it's just to like what's known as like reduce the inflectional form of words into like their base form. And then stop words are basically just extremely common words. And this again goes back to the idea of Zipf's law. Zipf's law is basically if you take the rank order distribution of word frequency, so like what are the most common words in, say, the English language, and you rank them by how often they occur, the word the appears with like the most frequency, and then there's like basically a predictable distribution of words. It's something like basically like 90%, or like 90% of what we say uses the like 100 most frequent words. Anyways, all to say, with respect to stop words, we want to remove words that are just extremely common and don't mean much, like don't add much to the semantic meaning of a sentence and these other things. So the words like and, the, a, we don't want to necessarily include those, because you can think of them kind of as like word type noise. So we remove those. And again, stop words is usually just like a vocabulary that's known. It's like we have a dictionary of known stop words. Take a sentence. If you see these words, like take them out. So it's like, it's actually a pretty easy, straightforward thing. Then regular expressions. I think almost every single one of you should have been at least exposed to these at some point. It's particularly relevant in the NLP, because we want to filter things and modify things based on like pattern matching. So this one I won't spend too much time on, but like basically you can just like use regular expressions to filter out like punctuation, or like modify, or like you know, clean out or identify if there's like email addresses. Do you want this like kept or removed? Are things within brackets, and so on and so forth. So regular expressions are used pretty heavily. And then these last two are more like, well, they're actual like techniques. They're ways of representing text in a way that you can then feed them into a model. So bag of words is usually the most simplistic. So again, because machine learning algorithms can't work directly on text, we need to convert them into, again, vectors of numbers. And bag of words is quite literally just the frequency of occurrence of a word within a document. So it's just like, how often does this word appear? And it's just like basically a count for each. And you can do that at the document level. You can do that at the sentence level. I think we actually show one of them at the sentence level. Yeah, and then this last one is a bit more of like a refinement. So this is TF, IDF is like term frequency, inverse document frequency. So it's a bit of a refinement on bag of words in the sense that so the idea here is that the most frequent words in a document tend to have like very high scores, but that doesn't necessarily lead to much informational gain. That's kind of like the idea. If we don't remove the stop words and the and a, if they occur so frequently and they have these really high bag of word scores, that doesn't actually help you do much after the fact. And so removing the stop words, you can kind of extend that also to other words that appear. So it's basically a statistical measure to kind of evaluate the importance of a word. So it's like if a rare word occurs within a document, or if there's a word that appears within a document that's not seen elsewhere, it tends to score higher because it has like more, I guess, semantic importance or informational importance to that one document. All to say, we're going to like actually like cover these things. The Nltk, so the natural language toolkit, is basically going to be your go-to for most like processing of sentences. It basically has all these methods built in. So for the first sentence tokenization, I've split this up as like a string block just so that you can visually see it. But this is basically like just a long continuous string, right? I just like broke it up into these component sentences to show you what they actually are. But you could just as well represent them as like this one long string. So when we run this through, we basically just like tokenize it into sentences. So for each sentence, like literally print them out. So you can see that 0th index would basically have the first string, second, and third. And so then for each of those, we can then go on and turn them into other like component breakdowns. So that's where we would do something like word tokenization. So here again, so here sent tokenize is just like sentence tokenization. Here word tokenize is for each sentence. Literally do the same. And so we end up with a readout of a list of these things. And like note as well, punctuation in these types of things end up being like considered their own word, whether you want that or not. Again, it's all part of processing. Yeah, anyways, then text, lemmatization, and stemming. Here, so it's basically, we basically import this like port stemmer and this like WordNet Lematizer. And here we like basically compare the two. So what I wanted to show is like the input word here is seen. Your stemmer, when you apply the different types of like stemming rules to it, will just simply return seen. Whereas the Lematizer will actually convert it to see, which is actually as a verb is I guess the more correct like form of it. But seen is still good, but see is maybe what you actually want. The same goes for drove, past tense of drive. So if you pass it to the stemmer will again return the word drove, whereas the Lematizer being a bit more intelligent, I guess, or like refined in converting basically words into their component forms, will feed you back drive. But yeah, anyways, the two can be used more or less in combination. And then stop words. I mean, here we're literally just importing the stop words and like printing out those that exist in the English language. So it's like I say, this ends up being a very, it's like an O1 type lookup. Well, maybe not O1 because this actually does have size. But if this was like a dictionary or like a hash map, this would be like just like an O1 process on to basically remove. And notice that there are certain things here like S's, T's are included for things like doesn't, or like, well, doesn't would be an NT, but like don't, for example. So if you split on punctuation first, you also want to catch kind of those overhanging elements. Like this is, again, all just like data cleaning and processing. Like for most natural language processing applications, if you go into like something like industry or whatever it might be. So Josh asked, would lemmatization use context and avoid things like lumping? I'm guessing that's just drive with drive, driving, driven. Yeah, exactly. Lemmatization has the keyword like lemma in it. So you actually end up like kind of building in like certain types of rules basically to, it's basically, just think of it as like, I guess, like a more refined stemmer. It tries to, it uses these drivel. Okay, so do you mean drivel as in like literally the word drivel? Because in that case, I don't think so. I think it would actually, I don't think it would consider it a drive, driving, driven. I'm actually not sure. I haven't actually done much of this NLP like pre-processing stuff in a while. I really touched on this in like 2018 when I was doing stuff on electronic health record processing stuff. So yeah, I don't know if I have a good answer for you. So yeah, it's like avoiding the trap of lumping it because it contains drive, even though it's unrelated. Yeah, I don't know. I'm sure there are edge cases that I can't fully appreciate, and I'm sure those who do this daily can. All to say, I guess it'd be something to explore with. But yeah, anyways, all to say, yeah, like lemmatization, I think, was what I had used predominantly at the time, just on the basis of it was better. And like stemming, I think you can do like stemming first, then lemmatization. Whether doing one before the other helps or doesn't help, I think is like fully up to practice and application. Anyways, all to say, yeah. So stop words themselves, when we want to remove them, it's literally this. We're going to word tokenize another like example sentence. And then basically this is as before, for those, again, just as a reminder, this is list comprehension. So like we want the word for each of the words if that word is not in stop words. So translated, for every word in our sentence, if the word is not in the stop words, give it to us, like return it to us. So that's like, give me this, where every variable, like variable name word in the list of words, which is our word tokenized form. Yeah, if it doesn't appear within this list, return it. So then we end up with, well, basically this. The words that we got rid of in this case are is, of, the, and it doesn't get rid of, so it doesn't do punctuation either. And that's actually, I guess, leading into the next point. When you might want to use something like regular expression to filter out something, perhaps like you can obviously filter after the fact your list for these kind of like one-off punctuation things. But something else you can do is basically just use a regular expression to pre-process that sentence before passing it into the tokenizer. So here we want to basically create a regular expression, and in this case, for those who are less familiar with regular expressions, we want this to basically match like not words. And so a not word in this case would be things like punctuation. So it would be this these commas here and this period at the end. When we run this and we print out the result, we basically get the exact sentence back without, and here we replace in a single space. So there's like a double space going on wherever there was a replacement. I guess there's like also an overhanging extra space here. Just for the sake of convenience, I like throw in like a bit of a reminder as to how you might build out these regular expressions, but there's a lot of stuff online to help you to that end. And most of the time, it's like you're filtering for something very specific. In this case, we're just doing punctuation. But yeah, all that to say, we're running closer to the end. I'll just touch on bag of words. So bag of words, you can use from scikit-learn a count vectorizer. Here's again another string. We run the count vectorizer, or we like initialize the count vectorize on it. We basically fit that transform. So we just like split out the raw text into its lines and get like a readout, in this case as a data frame. And here again, as a reminder, this is also by sentence. So when you look at, I like this movie, it's funny, I hate this movie, this was awesome, I like it, nice one, I love it. Those were each broken down into component sentences. And then each of the columns is basically the entire vocabulary of words that appears within that text. And so awesome appears in the first sentence exactly 0 times, in the second sentence exactly 0 times, exactly once in this next one, and so on and so forth. For those, if I don't know if I know I TA'd with I don't know if I've TA'd any of you in CISC 1005. I think I've been around Carleton long enough that I might have. But if you had taken CISC 1005 with Professor Bailey, there's the concept of a concordance. So if you actually like take the sum, so a concordance is basically a count of the number of times that something appears within an entire thing. So if you take the sum of each of these columns, you end up with a concordance. All of that to say, there's like there's ways that you can kind of bag of words something and then use it to like generate other types of transforms. That's just kind of like a shout out to, I don't know if I've TA'd you in the past, but yeah, anyways, all to say kind of like anyways, a good and fun way to represent these things. And as always, I highly encourage you guys to like take your own texts and like do some stuff, plot things. I don't know, from like a data just like analytic standpoint, just to be like, I'm actually curious to know how many times like awesome ends up. This kind of, again, also touches back on Zipf's law. If you guys are curious at all at seeing if Zipf's law holds with respect to, I don't know, your corpus of all your notes that you've taken over the course of this course, is kind of a, I don't know, I think of these things as fun. It's probably useless and dumb, but anyways, all to say, moving on from bag of words to something that may be a bit more, well, refined and useful. So TF-IDF, for term frequency, inverse document frequency, is basically this idea that we want to give a weight to a certain term X within a given document Y. So the frequency of X, so just like the number of times that it occurs, that term occurs within that document, is basically multiplied by this like other factor, which is the number of documents that contain X over the total number of documents. So it essentially just like adds extra weight to a rare word that appears within one document. If the word is like very frequent across other things, or across documents, so it's like less rare within one, it gets like kind of less of a score. Anyways, these are nice little like readouts as to like what that is. How you actually implement it is pretty straightforward. Again, it's just like a TF-IDF vectorizer, more or less following the same thing as above. And you can see that there's like a modification. Now you end up basically with more of a float type value for each term. Again, good for machine learning type applications where you want to then feed these into a given model for whatever type of task. But anyways, that basically covers the basics of what you would do for like processing text in NLP. Like I said, there's a lot of applications that follow after the fact. I'll briefly touch, I guess, on like basically for like transformers. Once I upload this, I think it's worth spending at least the time reading through a lot of the stuff. It actually touches on the concept of attention as well, like why transformers are so great. Has a lot to do with basically an attention mechanism. It'd be good to kind of at least have a high level understanding as to kind of how that works, even though most of these things have been nicely packaged, again, by the Hugging Face toolkits and APIs. This has a bit of history, so it's like you'll kind of recognize this as basically like Chris Ola's representation of recurrent, of like an unfolded recurrent neural network, which was kind of like literally 3 years ago, state of the art. Everyone was using it, and here we are a few years later solving the world's greatest grand challenges with now the transformer. Like I said, the stuff moves really fast. Yeah, so anyways, a bit of like history into that. And a lot of this is, so I borrowed a lot of this from one of the notebooks, which was touching on how you can actually create your own language model. So here, basically using a pre-trained model, we're using our own data set. So here, the example is like going from like, I think like English to Esperanto. So it's like you find a given data set, like you download it. Some of these things are timed, and they do take a bit of time. So I had tried to work my way through this last night, but some of these things will take like 18 minutes to run. Some of the actual model training will take about an hour. But just for the sake of like experience, I think it is worth kind of making your way through a notebook in one of these ways, just like appreciating that there are like special rare characters that you won't see in other things, and how those things get handled in a model. And also to try and like also think a bit creatively. Like a lot of I think like problems can be solved in industry and for different types of projects by just like kind of reformulating the entire thing as a different type of problem. So it's like I don't know, can you like figure or like solve some businesses like data processing thing by just like taking a huge data set of one type of something, treating it as a as like a new model or like a new language problem, and like just by doing it more or less intelligently and making sure that everything works. I think there's like a lot of like creative solutions that can be solved like broad spectrum by I guess like just having this kind of more unique take on things. But anyways, I'd suggest kind of working through these examples, or at least a few of them. What's particularly nice about this one is if you end up creating a new like model, like process or like language model all the way through with something completely unique, I don't know, you can always upload it. Like this is kind of what I really appreciate about Hugging Face, is they just make everything kind of like shareable, open, and accessible. You can like actually upload it to a certain place and see if people are downloading your Esperanto, well in this case Esperberto model for later use. With a couple minutes, I'm going to spend about maybe 3 minutes just on topic modeling in this one. I'm going to maybe append it to the bottom of this one and just add a few more takeaway messages. As always, I mean, these takeaway messages are more just on the pre-processing stuff. I highly doubt you'll have to know much or anything on the exam necessarily about like the ins and outs of, like, other than from like a high level what transformers are and maybe like attention mechanism, depending on whatever you guys covered in class. But I think really something to know much, or to at least be much more fluent in or understand is what each of these methods is or are. And then, yeah, so like topic modeling as just an example of something that you can do. Again, I didn't run through all of this myself, but there's another package, Gensim, that you can use for a lot of topic modeling thing. And again, a topic model is kind of a way to abstractly group your text and concepts within your text into kind of these abstracted topics. So like if I say I have a corpus of like magazines, and I know that they contain like science fiction type articles and like fashion and I don't know, like space, like basically if I know that those three general topics are covered within my data set, and I use like a topic model of like 3 different topics, I should expect generally most of the fashion articles tend to look alike. So they go under one of these like abstract topic categories. The space ones go into another, the science ones go into another. But some of the space and science one might like overlap. Like the idea is that you're like in a very unsupervised way trying to learn, like trying to group basically concepts and topics together based on the semantic meaning that your model learns of what's contained within these things. All to say, you do things like you tokenize, you lemmatize, you create a document word matrix. Sparsity tends to be a pretty common problem in natural language processing. There's one thing I think you should maybe keep in mind, I think for the exam, is just like how do you measure sparsity of like a given matrix or a data set, something more or less along those lines. Anyways, sparsity comes up quite a bit in machine learning, so it's good to kind of have an appreciation for that. But yeah, latent Dirichlet allocation or LDA models tend to be the kind of like go-to. It's basically a type of model that you can parameterize in a number of different ways. It's like a learning model that will try and basically minimize this measure of it's like an entropy derived measure known as perplexity, like how surprised is the model when it sees a new term or concept. So if perplexity, if its amount of surprise is very low, then it's like a good fit for that topic. If perplexity is very high, it's very surprised, it's maybe perhaps not a good fit. That's kind of like just very high level. There's an actual like numerical representation for what that actually means. But for the sake of time, I can't really like touch too much on it. But all to say, topic modeling is something that I think is valuable from like a data exploratory standpoint, trying to understand like what your data set contains. What's nice about this notebook is it kind of just like runs you through each of the examples. So if you kind of brought your own data set, you kind of get a sense for, again, like how a different document maps to a different abstract topic in this way by like, these tend to be float type values. So even though document 0 is a little bit represented in 7, it's mostly like topic 7 mostly pertains to document 1 and like a little bit to document 3. And you can kind of like draw that analysis across the board. And what's nice is like as you go on afterwards, you can actually see what is the I don't know. I don't know if this like ran through completion. Some of these matrices look kind of weird, but you can see like how often does a certain term or like word or concept map to a given topic, and within each of those topics, like by frequency, what are the more common words and so on and so forth. It's again, it's more of like a data exploratory type thing, but has a lot of like interesting potential use to try and just like figure out what is represented or what's covered within my documents or within all these things. Anyways, natural language processing is an entire field, and I can't cover it in an hour or half an hour. But I can strongly recommend that everybody kind of like, I don't know, you play around with it. It's the type of thing that if you ever go work somewhere in industry or whatnot, you'll be bound. Like text is like pervasive to society and to like business operations and whatnot. And as like an aspiring young machine learning NLP engineer, I'm sure like you can solve, like I say, creatively perhaps a lot of like either organizational issues or whatever it might be by just like, again, reformulating these things in interesting ways. All to say, that more or less rounds out what I had to present on. As always, all the best and good luck, both in the assignment 3, in the final exam, and then like onwards and forwards in life and your careers. I don't know if anyone has any, I don't know if I was checking the chat. I don't know if you guys had actual questions. Oh no, I think I'm good. Yeah, short of any of that, yeah, I do wish you guys all the best in everything that you go onwards to do. I look very much forward to evaluating what you guys put together for assignment 3. Because it's due on the 11th, which is the last day of class, there's no real like time to kind of celebrate whoever has the most exciting winning thing. But once I've kind of compiled all the results and myself, I'm pretty excited to see how everything boils down. What I'll probably do is just create like an asynchronous video that you're welcome to explore or like watch at your own leisure at the end of the course or after the exam or whenever it might be. But I'm hoping to kind of like do a fun, I don't know, here are each of the winners by like your group IDs and so on and so forth. And I don't know, it'd be fun. It'd be nice for whoever wins kind of gets like an opportunity. I don't know how you can like gloat from a distance, but I don't know if there's like a thread or something on So You Learn. Maybe that'd be an interesting opportunity to do so. Okay, so Josh asks, oh, has the weight of the model's performance? Not yet, because I don't. I'll be as generous as possible. I don't think the competition weight will be too high, because what you're being really evaluated on is like what you actually produce. So how much the like performance will, or like how much your competition performance will do. Like it's not going to be like whoever's in like last place or like tied for middle or last place won't end up. So if you're the worst model, do you get a 0 for that part? Yeah, that's the thing. I don't want it to be. It's going to be like, say maybe like I don't want to put any number on it, but it'd be something like 10% of the grade. If you're the top ranked, you get 10%, and then it kind of goes down from there. The idea of at least having a competition is to really encourage you guys to try and come up with as good as a can. The competition weight be bonus marks instead? Yeah, I'll talk to Jim about it. It actually doesn't even have to be part of your mark either. It could just also be a thing for fun. I do want to make this like obviously as fair as possible. If you're actually being evaluated on actually producing a final working and functional model for the course, I think we could just do it as bragging rights as well. Just out of curiosity. I'll talk to Jim about it, because I know he has run the competition in last year, which was the first offering of the course. And I think part of it was tied to the grade, so I'll see what he did then. But yeah, trust me, it's not going to be this won't fail you guys. I tend to be I try to be as generous as possible. It's kind of why I like open-ended assignments, because really all I want to see is that you guys understand what you're doing, how you can kind of put put models together, test things out, make sure that you kind of like holistically and fully understand what's going on within the machine learning field. And as long as you guys can like generate interesting and exciting things, then I mean, that's as like good as getting marks as I think anyone should for a course on machine learning. So I hope that kind of like clarifies things. Maybe it doesn't. I'll talk to Jim and maybe like specify that later on. As for what that affects you guys, I'm not sure it really does. Just keep like, I don't know, producing the best that you can in your work. And again, I emphasize just make sure it's functional. At the end of the day, if it doesn't work and I can't evaluate it, then it's a bit harder to I don't know, if I like can't run it, that becomes a bit trickier. But as long as everybody has something functional at the end of it all, and that is justified in what you did experimentally and so on and so forth, yeah, it's really just you'll be evaluated on that. Does anyone have any other questions? We're up against time. I'm going to stop the recording now. So